Which of the following wavelength will produce standing waves on a string that is 3.5 meter long? We know that the standing wave is the resultant of the superposition of two propagating waves that have the same wavelength. Along a string whose length is given, there are many possibilities for a standing wave to take place, but the wavelength should satisfy the following condition: n lambda over 2 is equal to L. Okay, now we are looking for lambda, so that's why we have to work out this equation so that we get an expression of lambda equals something. So in the first side here, lambda is multiplied by n over 2, so we multiply by the reciprocal 2 over n both sides to eliminate the coefficient of lambda and get it 1 and let it be 1. So lambda is 2l over n. So this is the expression. For this case, L is given to be 3.5 meters, so 2 times 3.5 meter over n. Now the least possible standing wave is one loop, which corresponds to n equal to 1. So I'm gonna call it lambda 1. 2 times 3.5 over 1 is 7 meters. Does it correspond or does it belong to the given choices? Yes, it's part D. Now the other possible one, as we go higher, n equal to 2, this means the frequency is increasing. The wavelength decreases, and you can go back and check the figures of the notes you wrote on your copybooks. As n increased, the frequency increased, and the wavelength and the distance between the consecutive crests decreased. So here for n equal to 2 times 3.5 over n equal to 2, which is 3.5 meter. Okay, also it corresponds to the given choices. It's choice B. So you see, as n increases, the lambda decreases. Now for n equal to 3, substitute for 3, it's 2.33 meters. Does it belong to the given choices? No, it doesn't. Okay, now if you check the given choices, we have 3.5 approved and 7 meters approved. We still have 5 meters and 1.75 meters. But concerning 5 meters, we can directly eliminate it because it belongs to the interval between lambda 1 and lambda 2. So as long as it's not equal to one of them and it belongs to the range or to the interval, okay, but doesn't equal to the boundaries, this means that it's not possible. Okay, and we're not going to obtain 5 meter because we said that as n increases, lambda decreases. So 5 is already greater than 3.5 and 2.33. So that's why we can eliminate it. So we're left finally with A. Now we take n equal to 4. Lambda 4 is 2 times 3.5 over 4. It's 1.75 meters. So yes, it is approved here. Now for the other 146, another exercise, you dip your finger into a pan of water twice each second, producing waves with crests that are separated by 0.15 meter. Determine the frequency, period, and speed of these water waves. Okay, so we have now to explain it. So this is it. Okay, so you dip your finger into a pan of water twice each second, producing waves with crests that are separated by 0.15 meter. So you are given more than one value. You are given that when you dip your finger twice, this means that how many oscillations are done? N equal to 2 oscillations. During how much time? During delta t equals 1 second. What is the distance separating the two crests? What does it represent? It represents the lambda, 0.15 meter. Determine the frequency, period, and speed of the wave. Now from the given here, you have that F is equal to N over delta T. So N is equal to 2 over 1 second. So it is equal to 2 Hertz. Now this is the frequency of the vibratory source of wave. So this is the frequency of the vibratory source, which is the hand. But we know that F frequency of the vibratory source is equal to the frequency of the wave. And you are asked to find the frequency of the wave. So it's equal to 2 Hertz. Okay, now determine the frequency done. Determine the period. We can deduce the period from the frequency. It's equal to the reciprocal of the frequency. So T of the wave is 1 over F of the wave. Here 1 over 2 Hertz. 0.5 seconds. And the speed of these water waves, so you have lambda, you have f, v equal lambda times f or lambda over t. So lambda times f is equal to 0.15 meter already given in the SI unit times the frequency calculated also in the SI unit. So it is equal to 0.3 meters per second. So the obtained value is in the SI unit of the speed. Now a sound wave traveling at 346 meters per second is emitted by the foghorn of tugboat. An echo is heard 2.60 seconds later. How far away is the reflecting object? This is a sound wave here. Okay, this is the sound wave. This is the barrier. Okay, the reflecting object. So this is the reflecting object. This is the reflecting object. Okay, the sound wave goes in this direction, covering this distance until it hits the barrier. Then it is reflected. I'm going to use another color here to represent the reflected wave. Then it is reflected, okay, covering the same distance. How many times? So this distance is covered. This distance is covered twice. Okay, so the echo is the reflected wave. So the time needed for the wave to go to cover this distance in a forward direction and a backward direction is 2.60 seconds, and the speed is 343 meters per second. So how far means you have to calculate d. D is the distance between the source. So this is d, between the source and the barrier. This is all d. Okay, so the wave covers 2d. That's why we write b is equal to 2d in this case. We call it d, 2d over delta t. Then you do cross multiplication. V is actually v over 1. You do cross multiplication. You get that 2d is equal to v times delta t. Divide by 2 both sides. 2 and 2 cancels here. So d is equal to v times delta t over 2. Do the substitutions. 343 meters per second already given in the SI unit. And the time is 2.6 seconds also given in the SI unit. And 2 over 2. So the answer is, I hope that you do not copy until you watch the video, so that you can understand the handwriting. Times 2.6 over 2 is 445.9. 400. So D is 445.9 meters. Now the other one, The notes produced by violin range in frequency of approximately 196 Hz to 2637 Hz. Find the possible range of wavelength in air produced by this instrument, knowing that the speed of sound in the air is 340 meters per second. The notes, so as we said, the range of frequency is as follows. You have to find the range of wavelength. Here it's a very important note I would like to give here, a very important note, is that keep in mind that in the same medium, the frequency and the wavelength are inversely proportional. For example, here when we say this is the range of the frequency for the violin, this means that we can express it as such. F for the violin, F of the violin, okay, the frequency is greater or equal to 196 Hertz or less or equal to 2637 Hertz. Okay, so we call this to be the minimum limit, of F, and this is the maximum limit of the frequency. This means that the minimum limit of frequency corresponds to the maximum limit of wavelength, and the maximum limit of the frequency corresponds to the minimum limit of the wavelength, because they are inversely proportional. Okay, because they are inversely proportional. So now this maximum frequency corresponds to the minimum wavelength, and the minimum frequency corresponds to the maximum wavelength. So we express it as such: lambda for the violin should be greater or equal to lambda minimum, or less than or equal to lambda max. Now we have to find lambda minimum and lambda max, each one alone. Lambda minimum, because V equal lambda times F, then lambda equal V over F. Lambda minimum is equal to V, that is given in air, because we are studying the propagation of the sound in air, over F max. And on the other hand, lambda max is equal to V in the air over F minimum. So it's equal to 340 meter per second over 2637 Hertz. (340 meter per second over 196 Hertz. Find the values. So we have 340 divided by 2637. It is 0.128 meter. Okay, I lost the pen. 0.128 meter, 128 meter. And the other one is 340 divided by 196, which is 1.73 meter. 1.73 meter. So now we can write the range as lambda for the violin is greater or equal to lambda minimum, which is 0.128 meters, less than or equal to 1.73 meters. That's it.